Good morning, everyone. This is Siri Chandana. Today I'm going to talk about mathematics for computing. The subject is mathematics for computing. My roll number is 24951A05BM. I am from Computer Science and Engineering. Today I'm going to talk about graph matching using the interference of discrete time quantum walks, exploring a novel approach to a fundamental computational challenge. The challenge of graph matching. Graph matching is the process of finding correspondences between the vertices, nodes of two graphs. It's a foundational problem in computer science with widespread applications across various fields. In chemistry, identifying smaller molecular structures, drug discovery. Next is, it is also used in uh, uh, pattern recognition, matching shapes, objects, or features in images. Network analysis, detecting similar patterns or subgraphs in social, biological, or technological networks. Uh, Classical methods often struggle with the inherent complexity and noise present in large or inexact graphs, leading to computational bottlenecks and suboptimal solutions. Quantum walks, a new paradigm. Quantum analogs and two main types and the coin space. First we'll learn about quantum analogs. Quantum walks are the quantum mechanical counterparts to classical random walks. They leverage quantum phenomena like superposition and interference. Two main types. The two main types are uh, yeah. Continuous time quantum walks, CTQW, defined by Hamilton dynamics. Discrete time quantum walks, defined by iterative operations on a state vector. Uh, Next is uh, the coin space. DTQWs introduce uh, an extra coin degree of freedom. This allows the quantum walker to exist in a superposition of directions at each step. Why discrete time quantum walks? It is a four. That is, first is the bipartite hybrid space, next is coin operation, and then shift operation, and last is interference patterns. Bipartite hybrid space, DTQWs evolve on a combined hybrid space representing both the position of the walker and its internal coin state. Next is coin operation. A quantum coin operator is applied, putting the walker's direction into a superposition of possible paths. Next is shift operation. Based on the coin state, a conditional shift operator moves the walker to adjacent nodes. Fourth is interference patterns. Crucially, because the walker explores multiple paths simultaneously through superposition, these path interference. This interference encodes information about the graph structure. The unique interplay of coin and shift operations and DTQWs allows for the emergence of rich interference patterns which are key to their computational power. What is graph matching? Graph matching is a problem of finding a correspondence between nodes of two graphs that preserves structural similarity. Applications are pattern recognition, bioinformatics, and social network analysis. Its goal is to determine if two graphs are isomorphic, that is structurally identical, or find the best alignment between them. Next is constructing the auxiliary graph for matching. Topper form graph matching using DTQW, a specialized auxiliary graph, is constructed. This graph effectively combines the two graphs we wish to match. Combining graphs. The two original graphs G1 and G2 are integrated into a single larger auxiliary graph. Auxiliary vertices. Each vertex in G aux represents a potential pair of vertices from G1 and G2, signifying a possible match. Connecting possibilities. Edging in G aux connect these pairs based on their structural consistency. Uh, if this is example for the constructing the auxiliary graph matching, these are the examples. A DTQW is then simulated on this G underscore aux, allowing the quantum walker to explore all possible matchings in a state of superposition. Quantum inference reveals matches. Interference amplitudes. The final state of the DTQW yields probability amplitudes on each auxiliary vertex. Higher amplitudes indicate a stronger likelihood of correspondence between the original graph nodes. Next is consistency measure. A robust consistency measure is derived by combining these interference uh, patterns with the agreement of edges between potential matching pairs, exact and inexact matches. This allows the algorithm to detect not just perfect, exact matches but also highly similar. Inexact graph matches 3 crucial for real world data with noise or structural variations. The unique properties of quantum interference provide a powerful mechanism to identify the most probable and consistent mappings between complex graph structures. Why quantum walks for graph matching? Quantum walks are quantum analogs of classical random walks. They leverage superposition and interference, enabling richer dynamics than classical walks. The evolution of quantum walk depends on the graph structure, so comparing interference patterns helps compare graph. Descriptor consists of position space, that is nodes of the graph, and coin space determines the direction of the walk. The state of the walker, the evolution. Here C is coin operator and S is shift operator. Using interference for graph matching. The interference pattern of graph of quantum amplitudes after several steps, depending on graph structure. Steps in these experimental results, molecules and images. NCI molecule database tested on graph representing molecules from the National Cancer Institute database. The DTQW approach demonstrated its power by reducing the permutation space by factors ranging from 10 power 20 to 10 power 30, vastly simplifying the search for matches. COIL 100 image delivered graphs applied to graphs delivered from the COIL 100 object image database. The algorithm showed remarkable robustness to structural errors and noise interest inherent in real world image data. These results highlight the scalability and superior noise tolerance of the DTQW method compared to traditional classical algorithm, paving the way for practical applications. Comparison with continuous time quantum walks. Rich dynamics. The inclusion of a coin space provides finer control over the evolution and richer dynamics, allowing for more integrate interference patterns. Next is interference control. Officers greater ability to engineer and harness quantum interference for specific computational tasks like distinguishing subtle graph differences. Handling inexact matches demonstrate distinct advantages in identifying high quality matches even when grades are not perfectly isomorphic, crucial for noisy real world data. Next is Hamiltonian dynamics. Evolve according to a time independent Hamiltonian often leads to similar dynamics without an explicit coin. Less control. while also leveraging quantum effects that generally offer less direct control over interference patterns. Potential for inexact matches can handle inexact matches to some extent, but DTQW's framework offers a more robust solution in this regard. Next is broader implications and future directions, and then conclusion. Quantum walks transform graph matching. Uh, Harnessing quantum interference, discrete time quantum uh, provide a powerful mechanism to solve highly complex graph matching problems by leveraging the nuisance effects of quantum interference. Enhanced performance. This approach offers significant reductions in computational complexity and, demonstrably improved robustness, particularly when dealing with noisy or inexact graph data from real world sources. A promising step. The success of DTQWs in graph matching marks a crucial step forward in the development of the practical quantum algorithms, paving the way for advanced analysis in diverse fields. Thank you.